Every day, whether or not people are aware of it, they experience processes controlled by integrated circuits. Infineon Technologies develops logic and memory components. Around the globe, experts in research and development centers are working on new semiconductor and system solutions. Production takes place in leading-edge manufacturing facilities worldwide. Up to 1 billion transistor functions fit on a silicon chip, only 1 square centimeter in size. The watchword for the future? Smaller, faster, more efficient. This is the raw material chips are made of. Sand. It is made up of silicon dioxide. Silicon is the second most common element on the Earth's crust and only exists in bonded form. Complicated chemical and physical processes are needed to convert silicon into a crystalline form and make sure the crystals will meet all the requirements necessary for chip production. The final product is a monocrystalline silicon rod of highest purity. This means the rod has only 1 impurity atom for every 10 million silicon atoms. Silicon is a semiconductor. Its atomic structure looks like this. Each silicon atom has 4 outer electrons. There are no free charge carriers. The pure silicon monocrystal is non-conductive at room temperature. To make it conductive, small quantities of specific impurity atoms such as phosphorus are built in. Phosphorus has 5 outer electrons. The 5th phosphorus electron built into each molecule of the silicon crystal lattice can move freely. Because of this structure, the silicon phosphorus crystal is negatively charged, or N-conductive. Boron atoms, on the other hand, have only 3 outer electrons. When they are built into the silicon lattice, 1 silicon electron is missing. This creates electron holes. They move through the crystal like positively charged electricity particles. The material is positively charged or p-conductive. The transistors in modern memory chips are constructed from p- and n-conductive layers such as these. Transistors are the smallest control units in the microchips. In the heart of an NMOS transistor, for example, we find p- and n-conductive layers of silicon crystals. An additional layer consists of silicon oxide and acts as an insulator. A layer of electrically conductive polysilicon is applied on top of it. Every transistor has 3 connections. The middle one is attached to the gate, the electrically conductive polysilicon. If we apply an electrical charge only to the 2 outer connections, electricity is unable to flow. The transistor is blocked. Things are different when an additional charge is attached to the middle connection. The electrons from the p layer now wander toward the middle connection and accumulate at the border area between the silicon crystal and the insulation gate oxide. A channel through which the electrons can flow is formed between the islands of n-conductive material. The electrical circuit is closed. The transistor can be switched back and forth between current off and current flow, that is to say, between 0 and 1. This binary system is the basis of electronic data processing. One highly complicated component, for example, is this dynamic 1 gigabit memory chip. On an area of only 1.3 centimeters, it can store the contents of 64,000 standard-sized sheets of paper. If it were constructed of conventional components, it would cover the area of a small town. Layout and design are at the beginning of chip manufacture. The large number of components calls for an elaborate design process to define the circuitry functions of the chip. Next, the technical and physical characteristics of the chip are simulated and its functions tested. Up to 1 billion transistors per chip are connected with the aid of wiring tools. The design tool forms the connection to a three-dimensional architecture of sandwiched layers. This construction plan is transferred to masks. These are reprographic stencils for the subsequent manufacturing process. The cover precision of the masks is monitored by a measuring machine, which can detect deviations in the range of 100,000th of a millimeter. The finished masks are the geometric image of the circuits that are exposed, one after another, in several production processes. The flawless production of microscopically small structures calls for a virtually dust-free environment in which the temperature and humidity are stable. The clean room meets these requirements. Here, in 10 liters of air, there is a maximum of only one dust particle larger than 1/2 micrometer. Not even the purest mountain air can compete with that. The ventilation, filtration, and supply area in the clean room is extremely elaborate. Here, 5.2 million cubic meters of air are circulated every hour. Hundreds of air volume regulators maintain a constant airflow. The silicon wafers are transported from the 300 millimeter fabrication in hermetically sealed containers, clean rooms inside the clean room, so to speak. This helps reduce costly filtration technology. The high technological standard, closed material circuits, and energy reclamation keep environmental stresses to a minimum. Supply systems with special containers and filters maintain the extremely high purity of the chemicals. The basic material for the chips is a 1 millimeter thick silicon wafer. This is a tiny cutout of a wafer edge, 1/4 of a micrometer. First, the conductive or non-conductive layers are produced by oxidation of the surface at approximately 1,000 degrees Celsius in a high-temperature furnace. A drop of photoresist is uniformly distributed by centrifugal force on the oxide layer produced, thus creating a light-sensitive layer. Special exposure machines, so-called wafer steppers, transfer the masks by exposure to the silicon wafer. The accuracy of adjustment to the features already produced must remain within a tolerance of 1/100th of a micrometer. Next, the photoresist-coated wafer is exposed through a mask. The exposed section can be developed, while the unexposed feature remains. The oxide layer is etched off. This etching process is carried out either by wet etching or plasma etching. In plasma etching, special gases combine with the layer to be removed. This makes it possible to remove the microscopically thin layers inside the windows created by exposure, development, and etching. After dissolving the remaining photoresist and then cleansing, another oxidation takes place. This time, a very thin layer is affected. Electrically conductive polysilicon is deposited on this insulation layer. Then, once again, photoresist, mask, and exposure occur, and the exposed photoresist is again dissolved. Then the polysilicon and the thin oxide layer are etched off. They both remain intact only in the middle under the resist layer. In the next step, an ion implanter shoots impurity atoms into the silicon. This changes the conductivity of the exposed silicon by fractions of a micrometer. Structure widths, distances, and cover precision are constantly checked. After the residual photoresist has been removed, another oxide layer is applied. Once again, the cycle of photoresist, exposure, removal, and dissolution takes place. Contact holes are etched in to open up access to the conductive layers because the contacts and interconnections must now be deposited. For this purpose, metal compounds are sputtered onto the wafer in sputtering machines. Once again, photoresist and mask. Depending on the component, over 200 meters of interconnections are created. The unexposed strips show the path of the aluminum conductor tracks that remain behind after the etching process and provide the contact to the underlying layers. More and more often, aluminum interconnections are being replaced by copper ones because the outstanding electrical conductivity of copper guarantees an extremely high data transfer rate. The insulation layer above the interconnections must be given a smooth surface, which is why the CMP, the chemical-mechanical process, is used. Excess material in the micrometer range is polished off. In this production line, the individual work processes are repeated 400 to 500 times until the integrated circuit of a component is completely assembled. Almost 500 1-gigabit chips have been produced on a 300mm silicon wafer. None of these chips is any larger than a single key on a computer keyboard. Molded into a plastic housing, the microchip is used for several thousand applications. Over the past few years, the chip connections have changed considerably. On the first plastic microchip housings, holes still had to be drilled in the printed circuit boards. The later housings can be directly soldered to the surface. To save space in the circuit boards, the connections in the latest construction forms are located on the underside of the component. This way, over 1,000 connection contacts can be realized. The third dimension is already being used for highly complex logic components. Sandwich chips are supplied as complete units. All the production phases of chips are controlled by researchers and developers using scanning electron microscopes. The comparison with a human hair shows us the dimensions of today's microelectronics. The checking and flaw analysis equipment is just as precise. For test purposes, a focused ion ray drills precise holes in the connection, allowing intervention into the completed circuitry. The supplementary interconnection being inserted into the circuit here is only 1 micron wide. Chip development has become the pacemaker of our economy. Microelectronics is the key industry of our modern information society. Thanks to microchips, our lives have become more mobile. Worldwide networking makes everyday professional life easier. The technological accomplishments of modern telecommunications depend primarily on progress in the semiconductor industry. Microchips provide convenience and simplify the storage of images and data. Microchips recognize people and correlations. Microchips make vehicles more efficient and even safer. Infineon Technologies is at the forefront of the industry and sets standards for the latest cutting-edge technologies. Never stop thinking.